First of all, I would like to say that we have 50, and this is the other one, 59 students in the class that are that have connected, but only 50, so 2 students have not tried at all to connect with TapHat. So if you guys have, or girls have, a problem with a connection to TapHat, let me know, because obviously by not connecting, by not doing those, if your problem is consistent, by not doing these problems, then you're gonna lose a lot of points. Number 2, first of all, this is transmission matrix. It's a definition of the transmission matrix. So even if 86% of the class was able to respond well, I think the goal when it comes to definition of matrices or definitions is to have 100% success. All right, so without 100% success at the fundamental level, going higher in concepts is going to be even more problematic. So those of you who responded to B or C as the correct, please do me a favor and try to go and revisit the definition of the matrix, of the transmission matrix, and then make sure that you know that is going to be absolutely critical. Now, going to the transformers, we have a more serious problem. The fundamental transformer is something that you have probably seen multiple times in circuits, and I know it's all theory, but it's extremely important. So I would like you, those of you, the correct answer here, if you want to see, is the one B. All right, so I would like the others who have, and there was a very large percentage who selected the wrong answer, I would like you to go and review that topic, because on Wednesday or Friday, I'm going to give you yet another problem that has both of these concepts in there. And I would like to make sure that in this other problem that has both concepts involved in there, then you're going to be able to respond to it. The reason I decided to give you these 2 questions today is because as I was checking the quiz, for which I gave you 6 hours after our class, and I know 6 hours for some of you who may work, you know, but it gives more than 5 minutes, definitely. Again, only 54% of the class got it correctly. And the correct answer is this one. So I would like you to know how to solve this problem. Well, I will put answers to those today or tomorrow on under eCampus. But this, if you exclude, because in reality, this problem that I gave you here is nothing else but a combination of the 2 problems that I gave you today. So obviously, the biggest issue that we have is here with the transformer. Not so much with the definition of the transmission matrix, but the transformer itself. So please do me a favor, review the fundamentals on transformers. For those, I believe that you have done those things, this particular element, and then make sure that we understand, we know how to use it. Any questions? I just wanted to share with this with you, just to make sure that to see what I see, and so to make sure, we need to make sure that we do things correctly. And I do worry about some of you not following up with the class. I'm telling you, for those who don't follow up with the class, it's going to be only very difficult at the end. Very difficult. and I will do the best I can to help you, but there is so much I can do to help you. You need to also help me help you. I mean, we need to do this together. Any questions before then I go? Any questions about any of these or any comments? Before I go and I start with some fundamentals of transmission lines and review some important concepts. One more thing that I wanted to say is that I will review a few concepts today, and if this new review is to help you with homework, the homework that you submitted yesterday, I'm willing to extend the homework until 9 p.m. today. I will change the due date so you're not going to be delayed, and you can resubmit some of your solutions on the basis of what I'm gonna show you, or if you get any more information that is gonna help you, I will open it up so you can submit it until 9 p.m. today. Okay, then we will go to our review.
Oh, Professor, I just want to make sure this was being recorded.
Yes, it is recorded. Do you see the recording? It is recording, at least I see that here.
Yeah, it says recording on the screen.
Yeah, okay. Perfect. I mean, it's recording on both places. One goes to the cloud, and the last time it recorded on the cloud only, so I need to know how to download it. But this time it records both on my computer and the cloud. All right, so I prepared a set of problems, but I thought they were so involved. So we'll take time to do this, and I have one problem here with a transformer. But I decided today I will upload that for Wednesday, but I decided today to do something even more fundamental. So I'm going to start working those solutions with you. And so you can ask me any questions, and I want it now. So to start with a fundamental of a transmission line, I'm not going to derive things. I will just tell you what you need to remember, and so to make sure that we are on the same phase, as they say. So this is a transmission line. And usually we characterize those with Z naught and beta. Okay, so this is a transmission line. And this line has a length. And the length of the line is L. And has a load. ZL, and is connected to a source. And as a matter of fact, I would like this source to have an internal impedance as well. Z sub S, and then the source here, V sub S. All right, now what we know about this transmission line, that the transmission line has a voltage and a current, but if you think, the way it works is the following. The voltage has a component that goes like that, which we call the incident voltage. And if the line were to be infinite long, that would keep going like this. But because the line is terminated, it also has a reflected voltage. Because of the incident and reflected voltages, we also have the respected incident and reflected currents. Also, there is another thing that we are considering for now for those derivations, even if at the end is not becoming that important. and that is the coordinate system. We assume that we have one dimension here, z. We assume that here is z equals 0, and we assume that here is z equals minus L. All right, so as a matter of fact, I need to move this lower, and this is minus L. So the positive z is to the right. Okay, having said that, then we have derived from before that v plus equals v0 plus e to the minus j beta z, v minus is v0 minus e to the j beta z, and then I plus equals I naught plus e to the minus j beta z, and I minus equals I0 minus e to the j beta z. What else do we know? That I0 plus equals V0 plus divided by Z naught. And that's how we define the characteristic impedance. And I0 minus is minus V0 minus divided by Z naught. These relationships you have to know by heart. You should not be looking to find them. This you need to know. Okay. Then, having defined those, we define another parameter, which is the reflection coefficient. And the reflection coefficient, gamma of z, in fact, is nothing else but v plus of v minus of z divided by v plus of z. So practically it's going to be v0 minus over v0 plus e to the 2j beta z. Okay, then what else do we define? The ratio v0 minus over v0 plus is nothing else but the reflection coefficient at z equals 0. And because that's where the load is located, we call that gamma L. And this one, you can prove that is equal to ZL minus Z naught over ZL plus Z naught. Also, these formulas you should remember by heart. If you don't remember them by heart, then you should do it. All right, we're not going to remember too many things by heart, but these are important. Now we are going to the concept of a stub. In fact, let me go first before we go to the concept of a stub. I would like to go to the concept of an input impedance since we are here. So in this one, let me use this one, and at this point I introduce the input impedance as a function of z. And what is the input impedance as a function of z? Is nothing else but v of z divided by I of z. And what I find is that this is equal to z naught ZL plus J Z naught tangent of beta Z divided by Z naught plus J ZL tangent of beta Z. Also, that you should remember it by heart. So these pages are the fundamental expressions You need to remember.
Excuse me, Professor.
Yes.
I have a question. Inside the tangent, is z the distance, like the length?
You see, now Z is, in this particular case, yeah, it could be, you can, exactly, it's the length. So it's not the coordinate, but it's the length, exactly. So let me, in fact, thank you for reminding me of that, to put it here. And let's assume this is a length D. In this case, is going to be D here and D there, and that is at Z equals minus D, which is so practically at a distance D from the load, at a distance D from load. Okay? And a distance D from load is really where, I'll be accurate here too, is where this is minus D. Okay. All right, so this you learn by heart. Now, let's talk about a stub. What is a stub? A stub is nothing else but a section of line which is terminated either at an open or a short. You have a section of a line, maybe a length of D or L, and then it's either open, so that's an open stub, and has a characteristic impedance Z naught, and this is the A prime, the input. Or it could be a short stub, shorted rather, or a short, not short for length, but shorted at the end. Okay, we call it short stub. And Z naught, here A prime, and distance D. Now, if we take the above formula, first of all, let's try to find this
Professor?
one. Yes.
Can I ask a question regarding the previous circuits?
Yes.
On which part of the circuit we have the reflection?
On which part of the circuit you have to do what?
We have the reflection.
Oh, the reflection can be at any point and is defined as at that point, Z is defined as the ratio of the reflected wave V minus over the incident V plus.
So for the reflection, the wave, the signal before propagating to the transmission line between ZS and the network, what's the ZL and Z naught for reflection formula?
ZL is the load, which is given, and Z naught is the characteristic impedance of the line.
Even for the reflection before the network transmission line?
The reflection where, you mean at the ZS?
Yeah.
At the ZS, now that's a good question because it's gonna help me to go to another thing. So thank you for asking this because it's gonna help me. I'll move that a little further down. Okay, now at this point, we have Z in at the beginning. Let's assume that this was A prime. All right, let's call this B prime. So Z in at A prime is just the input impedance to this transmission line that is terminated. And obviously that Z in at Z equals minus L is going to be equal to Z naught, characteristic impedance of the line, ZL, the load, plus J Z naught tangent beta L, where L is the length of the whole line, Z naught plus J ZL tangent of beta L, which in fact takes the previous circuit and makes it look like the following. You still have the source, Vs, the input internal impedance of the source, Zs, and here at A prime, A prime, we have this equivalent impedance. Why do I call it equivalent impedance? Because, of course, physically, it's not just an impedance sitting there. Physically, it represents a whole circuit, which is the transmission line plus the load. So this is an equivalent impedance, all right? Now, a question for you. Under what conditions we have, so the source is giving power to our circuit. Under what conditions we get the maximum power to be delivered to the circuit, which is the transmission line plus the load? Do you remember from your circuit theory what?
Equal impedance.
Which impedance?
Z in equals ZS.
Z in, it has to be the complex conjugate of ZS. Not equal, complex conjugate. This is what in phasor form you have seen from circuits, that we get the maximum impedance power transferred to our transmission line plus the load. And because the transmission line is ideal, does not have losses, I did not speak about losses, so all of this power is going to go to the load. Is that clear? Do you remember that relationship?
Yes.
Okay, perfect. So, if we are to optimize a circuit, and you can transfer like this, I give you this circuit, say, the top one, and I say, find the maximum impedance transfer, find the conditions under which you have, or find the length of the line, or find the Z naught, under which you have the maximum transfer of your power to your load. So practically, you will start with this relationship here. That's the fundamental. And then that's how you start. You say, if I were to know Z in at AA prime, then practically, I would need to, if I knew that, then I would need, how to find it? I would need to make that equal to the complex conjugate of ZS. If ZS is real, then it becomes equal to ZS. But if ZS is complex, as it could be, if your source is nothing else but a transistor that has also presents to you like the Thevenin equivalent of a transistor, it could be a source and a complex impedance, all right? And so I would need to make that relationship hold. And then I'm working backwards. I say, now how am I going to find this Z in at AA prime? So practically, I work like this. I go back to be able to find to these relationships to eventually find Z in. And after I found the Z in, then I will have to equate ZS. So to go a little lower. So practically I do here and say that finally I will have to solve the following equation. ZS is Z naught ZL plus J Z naught tangent beta L Z naught plus J ZL tangent beta L. Now, if ZS is real, RS, then practically I will equate this to RS. If it has if ZS has RS plus JXS, then I will have to equate my Z input to that, to in fact ZS complex conjugate, which is RS minus JXS, okay? And what am I gonna get out of this equation? What happens when you have an equation that involves complex functions or numbers? This one is a complex equation or equation that involves complex numbers. How many equations do I get from those?
2.
One that equates the real parts and the other that equates the imaginary parts. If I get 2 equations, then to have a unique solution to the problem, I will need 2 unknowns. And my 2 unknowns can be, so practically, I can say this one will give 2 equations, real equations, with 2 unknowns. Which are the 2 unknowns of my problem? L is 1, okay, the length of the line. And what is the other one?
The impedance of the line. Yeah.
Yes, exactly. The impedance of the line. Now, nobody tells you that you can find a solution to that, because that's the other thing that happens in designs, all right? You remember I told you that when I give you a design, it's not always true that there is a possible solution. So it is true that when you have to solve 2 equations with 2 unknowns, you can find 0 solutions, you can find 1 set of solutions, you can find multiple set of solutions. Is that correct? We've known that from linear algebra, right? So you need to be prepared that any of the above is possible. If you find 0 solutions, that means that that with a single transmission line, that matching of the load to the source could not happen. So that means you needed to include something more. So you need to make it something more complex. And that's where you're going to stubs. If you find multiple solutions, that means, yeah, there are multiple values of Z naught and L that can make this work. And then you have to consider other design restrictions then that will help you select. We'll talk about this later. I don't want, in fact, to mix this now, but be prepared that you may have, and in design that happens, that you may have any of the above, either 0 solution or 1 unique solution or multiples. Now, any questions so far before I move? Okay, now let's assume that I don't find a solution. And then I'm thinking, okay, I have my load. Somebody gave it to me here, ZL. They gave me one possibility, one line, section of line to match it to ZS, but I can't. What else do I have in my play toolbox? In my toolbox, I have the following possibilities. And I will, first of all, before I go to, I started with the stubs, so let me finish those. So I have in my toolbox the concept of a stub. And I said, as I said, there are two types of stubs, open and short. According to, so here is that Z, A prime for a stub, and then another Z here, just how I'm gonna represent them. All right, now for the open stub, open circuited, what do I have? I have, let me go from the ZA, from the initial relationship, according to the input impedance relationship that I have utilized. This one is going to be ZL, which is open, Z naught tangent, beta D, or Z naught plus J ZL tangent, beta D, which in fact, when ZL, when it's an open stub, ZL goes to infinity. Is that true? That's the equivalent impedance of an open end. It's infinite. So what happens in the numerator here when ZL is much bigger than J Z naught tangent beta D? Then I ignore this. And in the denominator, when this goes to infinity, I ignore that. So now, what do I get? I get here that this is equal to, let me see, yes, and then I have Z naught, ZL over J ZL tangent beta D, which is minus J Z naught cotangent of beta D. And now you need to always remember that the input impedance to an open circuited stub is this. Number one. What happens with a short circuited stub? We have now, again, that Z A prime stub is Z naught, the same now, ZL plus J Z naught tangent beta D over Z naught plus J ZL tangent beta D. Since ZL is short circuited, ZL is 0, which means that this and this go to 0. And from here, we have that Z A prime S equals J Z naught, this and this goes, Z naught tangent beta D. That's open circuit stub. This is short circuit stub. Why are those important? Now, if I have a load and I have a transmission line connected to the load, then I can put somewhere on this line, let's assume that the line continues here. I can put here a stub, and that can be open or short. And if the stub is open, it's going to give me ZAA prime S up here. If it's short, it's going to give me this one. Obviously, different values. So whether I'm going to choose an open or short depends a lot on this length and the load ZL. However, there is one more thing. This is equivalent to the following simpler circuit. This transmission line, and somewhere here, I have a shunt load, which comes from the stub. And that here is the load at the end of the line. Okay? So now I have already simplified my circuit. I have put here a reactive load, Z. And this reactive load is extremely important. If Z is reactive, then 1 over Z, which is Y, this can also be reactive. Okay? Which means I can either use an impedance here, or I can use its admittance. And whether I'm using an impedance or an admittance depends on the following. If I have a shunt configuration, like here, if I have a shunt configuration, then I'd rather use an admittance, because it's easier to add, and let's assume you have something else here, all right? It's easier, and something else here. It's easier to add admittances if they are in parallel. But if it's a series configuration, it is possible to add this stub in a series form. Then this is shunt configuration. So for a shunt configuration, it's better if we use Y. And in our case, for example, here, it would be a transmission line that has a load at the end. ZL. And if I were to find the input impedance here, from the load, which is given by the same formula, ZL plus J plus ZL plus, excuse me, J Z naught tangent beta L, if this is L here, and then Z naught plus J Z L tangent beta L. All right. Instead of using that, I'd rather use the Y in at L at AA prime, or yes, you can call that Y in at 8A prime, also Z in at 8A prime, or Y in at AA prime, which is nothing else but 1 over Z in at AA prime, which then, as we said last time, is nothing else but Y naught YL plus j y naught tangent of beta L over y naught plus j I L tangent beta L. And if I have that, that simplifies to the following. These two admittances in parallel, and this the total admittance, therefore, is ys plus y in a prime. Okay, and if I want to have an input admittance here, that is y in at that point, that let me call that ys, just a second to remind you of the homework. If I want to have that equal total, say, if I want to have that equal to 1/30 minus j 1/50 ohms minus 1, if I wanted to have that, then practically I will have to equate yt to ys plus y in at a prime. And that will give me what I need in terms of any specific components that I have, that I want to solve for. Now, this is very similar to what we did for your homework. And I don't want to go into more specifics and solve the problem here, but this is in fact the fundamental theory on which your homework was based. Because I saw that many of you had substantial difficulty solving it, I would suggest that you make sure you know how to solve this problem. Now, you still have until those who want, with the base, on the basis of what I said, those who want to go back and revisit their solution, you have the time to do this until 9 p.m. today. Those who have not submitted it yet can submit it. Those who submitted it, but now they want to make changes, you can resubmit. You have that option. So with that, any questions you may have?
I have a question. So in the questions, is the given yn the y total that you have right here at the bottom?
Yes. You're
That's
talking
not,
about?
yeah, it's not the complex conjugate or anything.
No, that was given. In this particular problem that I have here, I have not given you a source. All right. So I just gave it to you, like I did in the problem, if you remember, in the homework. Yeah.
Thank you.
You're welcome.
And on the homework, is it acceptable to use a Smith chart instead of the...
Sure, if you can do it, absolutely.
Cool.
If you want to use a Smith chart, yes. We are going to use Smith charts, but I decided not to introduce them at this point until we go later, and then I will do a review of them then. All right, so this is this is the fundamental theory that is going to be so important for us. And I will show you why this theory is so important and these equations that I want you to remember, because on Wednesday, we're going to solve problems on networks. And practically one very important thing for networks is to find equivalent circuits. Because if I can find a simplified equivalent circuit for a network that is very complex, then I can solve the problem a lot easier. So equivalent circuits are extremely important, and using matrices, specifically transmission matrix, because we can combine things. And then from the total transmission matrix, we can go to a total impedance matrix, because there are the formulas in your book. You can derive the formulas, but you can use them from the book as well. And then if you knew the impedance matrix, then we are going to see in equivalent circuits that from there, clearly and easily, you can get an equivalent circuit representation for a very complex otherwise network. Okay, so we are going to go there on Wednesday. We're going to do that on Wednesday. I hope you saw my email about my office hours. I'll stay online now up until 3:15, but then I have to take off and then I'll be back at 5.